Hello dear students, welcome you all. In this lecture, I am going to discuss about the Peltier effect. Right? Peltier effect. Right. This is the second thermoelectric effect that we are discussing here in this topic, that is the application of thermodynamics to thermoelectric effects. Right. Earlier we have discussed Seebeck effect. Right. So this is the Peltier effect. So this is called Peltier effect because it was discovered by Jean C. Peltier in 1834. So that's why this effect is named after his name, Peltier effect. So what is Peltier effect? Peltier effect is basically the converse, or we can say reverse of the Seebeck effect. But we have seen in the case of Seebeck effect, we have seen that when the two junctions of a thermocouple are kept at different temperature, right, then there is a production of electric current in that thermocouple. That was a Seebeck effect. Now here in Peltier effect, the things are reverse. What we are doing, we are taking a thermocouple, we are applying a source of current like a battery or cell in that thermocouple, and then we allow the flow of current in that thermocouple. So in this case, there will be production of heat at one junction, and there is production of cooling at other junction, right? So you can see here that the entire process is reverse. Earlier we were supplying heat and cooling at two junctions, but here heat is getting evolved at one junction and heat is getting absorbed at other junction, right? So to understand it in a better way, let's take the case of the thermocouple of a copper and bismuth, right? So this is copper right? This is the copper wire. Now I'm taking the bismuth. This is bismuth. Right. Now here we are going to apply a battery source of EMF in the circuit. Let this is sorry. Add here. Right. So this is positive and this is negative, right? This is copper and this is bismuth, right? So now this is the thermocouple. We have applied a source of EMF in this circuit and we are allowing the current to flow here. Current I is flowing in this thermocouple in this direction, right? So what will be the result? The result will be at this junction we will get heating and at this junction we will get cooling. sorry. So this junction will become hot and this junction will become cold. So whatever I said earlier, that in case of Peltier effect, when you take a thermocouple, you applied potential difference across this thermocouple by the application of a cell or battery, and you allow the flow of current in that thermocouple, then at one junction there will be a production of heat and at other junction there will be production of cooling, right? It means heat is absorbed at this junction and heat is evolved at this junction, right? Now you recall the Seebeck effect. You can see what we were doing there. We were not having battery here. We were having a galvanometer here in case of Seebeck effect, and at this junction we were heating. Clear? We were applying heating, and at this junction we were making cooling in case of Seebeck effect. So you can see in that case we were supplying heat at this junction. Heat was absorbed at this junction. But here in this case heat is evolved. Heat is coming out of this thermocouple at this junction. Similarly, in case of Seebeck effect, there was production of heat. So we are making cooling here, right? It means heat was evolved here in Seebeck effect. But here it is the production of cooling in case of Peltier effect. It means in this particular case heat is absorbed. So we can see that the Peltier effect is exactly converse to the Seebeck effect, right? You can say it is the converse of Seebeck effect, right? So this is now I'm hopeful that the things are clear. What is Peltier effect? Now I'm going to the Peltier coefficient. Now Peltier coefficient is defined as the amount of heat evolved or absorbed, right? At each junction when current some amount of current flow across this thermocouple for some period of time. So we will see how we will arrive at the Peltier coefficient. Clear? So let's suppose that I have a thermocouple and I allow the current I to flow in that thermocouple for a period of time t, right? Then let heat absorbed here. In this case, there is a production of heating. So it means heat is evolved here, right? So it means let q amount of heat is evolved here and q same amount of heat is absorbed here. So according to the study of Peltier, this amount of heat evolved or absorbed, right, it is directly proportional to two factors. One is the amount of current flowing in the circuit in the thermocouple, and the second is the time for which this current flow, right? So if I write it combinedly, then it will become Q directly proportional to I T. I can write Q is equal to pi I T. Here pi is proportionality constant and this is a Peltier coefficient. Clear? I can further define it. If I modify this equation, then pi becomes equal to q upon I into t. If I take I is equal to 1 ampere, t is equal to 1 second, then it becomes pi is equal to q. Clear? So we can define Peltier coefficient as the amount of heat evolved or absorbed at a junction, right, when unit current flow through the thermocouple for unit time, right? So this is the definition of a Peltier coefficient. I can write down the units of Peltier coefficient from here. It will be joule per ampere per second, right? So you can write in this way what are the units, right? So this is about the Peltier coefficient. Now I am coming to what is the reason for this production of heat and cooling at these two junctions, right? So to understand it, cause of Peltier effect. Sorry, cause of Peltier effect. Again, let's draw this thermocouple. This is copper. This is bismuth, right? Now, copper, and this is bismuth. So, I have told you earlier also that when I join two different metals together, there is always production of contact potential, clear, at the junction. This is the first junction, right, and this is the second junction. This is because the two metals have a different concentration of free electrons, different density of free electrons, different Fermi levels. So what will happen? The electron will start flowing from the metal that have high electron concentration to the metal that has a low electron concentration, and this process will continue till a stage is reached when one end of the one metal acquire positive charge and the other end, I can say here that this becomes positive and this becomes negative when these are joined together, right? Why? Because electrons are flowing from copper to bismuth, we can say. Then after some time the electron will come here, it will become positive here, it will become a negative here, right? Same situation will be there, right? Positive and negative. So after some time a kind of potential that we call contact potential will be set up at these two junctions. Contact potential, right? It will be set up at these two junctions, clear? Here again we have a contact potential when I join these two metals together to form a thermocouple. Now we know very well, we have seen in the case of Seebeck effect also, that now this contact potential is existing at these two junctions when I allow the flow of current in this thermocouple by the application of a battery. Let I have a battery here. I have applied a battery here. Suppose I apply this battery here now. Now what will be the effect? This is positive, this is negative. So when I apply a battery, so the current will start flowing here to here in this way. I, 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 and I. Clear? I have joined now these two. This is a thermocouple. Now you can see when the current flow through this entire thermocouple, right? At one point, at one junction, it is going from a higher potential to lower potential, whereas at the other end, other junction, it is going from a lower potential to higher potential. The things are exactly reverse. You can see even the flow of electron. Let current is going in this way, so electrons are going in this way. Clear? Right? They are moving in this way, right? So here electrons are going from here to here. It is positive, it is a negative, right? And it is negative, it is a positive, right? You can see here, right? So we can say that electrons are moving, when they are moving in this entire circuit, at one junction they are going from a positive terminal to negative, whereas at other junction they are going from a negative to positive. We know very well that positive terminal, we can say it is higher potential, we know very well it is higher potential and it is a lower potential. Clear? And it is again here higher and it is a lower, right? So you can see here that at one junction the electrons are going from higher potential to low potential. At the other junction, electron are going from lower potential to higher potential. So what is the natural tendency of the electron? Natural tendency of the electron is to go from lower potential to higher potential, right? So you can see when they are going from lower potential to higher potential, right, there is production of heat, right? But if they are going from a higher potential to lower potential against their natural tendency, it means there will be a absorption of it because they need additional energy. So that energy will be taken from the surrounding, right, and that junction will become cold. So this is the basic reason for the production of heating and cooling at the two junctions, right? Once again I'm repeating that if we look at this circuit, that at one junction you can see here electrons are going from higher potential to lower potential. Clear? Whereas here the electrons are going from because you can see the direction of current is opposite. So here electrons are going from lower potential to higher potential. They are going in this way, right? And the electrons have natural tendency to go from lower potential to higher potential, right? So at that junction where they go from lower to higher, energy will be evolved. But at that junction where we go from higher to lower, right, energy will be absorbed. It means heating will be produced at this junction and cooling will be produced at this junction. So this is the reason for the production of heating and cooling in case of Peltier effect, right? Now here is one thing is very important. If I reverse the direction of the flow of current, then what I have to do? I have to reverse the weight tree, negative, positive, right? In that case, negative, positive. So what will be the effect on the heating and cooling? It will get reversed because now the direction of the flow of electron will be reversed. So obviously the heating and cooling will be interchanged. In that case, this junction will become cool and this junction will become hot. Clear? If I reverse the direction of the flow of current, right? Now the current is going in this way and electrons are going in this way, right? So this is obvious, right? So this is, we can say that, Peltier effect is reversible. If I reverse the direction of the flow of current, then the junction at which heat evolved and the junction at which heat absorbed, they will get interchanged, reversed, right? So this is all about Peltier effect. We have discussed Peltier effect, production of heating and cooling, Peltier coefficient, and this is very, very important that we here explain what is the reason for it, right? So this is all about Peltier effect, right? So thank you very much.